Hello and welcome to Proving Things by Contradiction. Check out my intro to proofs video, and if you're just looking for examples, you can feel free to skip to the end of this video. So if you remember, a theorem is a statement that we can prove is true, and one way that we can do that is a proof by a contradiction, which is also known as an indirect proof in some books. So the general way that we prove things by contradiction is by assuming that the theorem is false, which eventually leads to a conclusion that's false. So for if-then statements that go like if this, then that, or P implies Q, we have to first negate our original P implies Q statement, right? Because that's our theorem. So we can use the laws of conditional identity to change it from this to this, and then use De Morgan's to change our or to an and then finally use double negation to change it from not P to just P and not Q. So really when we're doing a proof by contradiction, we're assuming that P and not Q is true, and at some point that'll give us a contradiction that shows that actually P implies Q is true. So for a general sketch of how this proof will look, first of all, we always state our theorem, and sometimes we rewrite our theorem as if-then. Then we say that we're proving by contradiction, and we specifically state the things that we're assuming are true. So for this kind of problem, especially if you've rewritten it as if this, then that, we're assuming that P and not Q are true. So in particular, that the hypothesis is true and that the conclusion is false. So if it were a if this then that statement, I would say that this and not that are true. Then, as always, we state some definitions. We plug our definitions into our statement, and we definitely do some manipulations. That can be arithmetic, that can be some kinds of multiplying by 1, where 1 is equal to k over k for two integers k, for an integer k that isn't 0. And then we should come out with some obvious contradiction. So sometimes that contradiction will look like whenever we do things logically using these two propositions, we get something out that directly contradicts our assumptions, or we get something that contradicts a known axiom or a known theorem. But usually the contradiction exists between something that's assumed and something that you get from logic. So let's do a first example with just words. So all fast food restaurants are relatively inexpensive. So we want to rewrite our theorem as if-then, just so it's easier for us to process. So I can say, if a restaurant is a fast food restaurant, then it's fairly inexpensive. And once again, you can always write these with quantifiers. I can say, for all restaurants that are fast food restaurants, they are fairly inexpensive. So this is a kind of universal generalization proof, and specifically a proof by contradiction. So once again, we'll say that we're proving by contradiction and state our assumptions. So I would say a restaurant is a fast food restaurant and it's fairly expensive. So our definitions are maybe a fast food restaurant is a restaurant that sells food that's cooked in bulk. And then another definition might be that food that's cooked in bulk means that there's less labor and bulk buying. And then another definition is less labor and bulk buying means that all the costs of maintaining this restaurant are lower. So then we plug our definitions into our if-then statement. Then we just plug our definitions into our statement, right? So a fast food restaurant uses less labor and bulk buying, therefore it costs less, and it is fairly expensive. So there's definitely an obvious contradiction in that statement, right? Costs less, which we got through logic, contradicts our assumption that the restaurant is fairly inexpensive, because costs less and fairly expensive are just evidently different. Let's do a quick example with odd and even numbers. So the statement is, for every integer n, if n squared is even, then n is even. So let's first out state that we're proving by contradiction. And you might be able to see that the reason that we're proving this by contradiction is because it's kind of hard to prove this directly. If n squared is even, we would write n squared as equal to 2k, but it's kind of hard to take the square root of 2k. It would just be not great to do by direct proof. And then let's state our assumption, right? We're saying there is an integer n such that n squared is even and n is odd. And then we can define our integer n squared and n as being odd or even in the ways that we've talked about previously. Next, we always plug our definitions back into our statement. So we can say that n squared equals 2j just by our assumption, but n squared is also equal to n times n, or 2j plus 1 times 2j plus 1 by substitution of 2j plus 1 equals n for some integer j. Phew. Then we can just do some manipulations that we see that n squared is equal to 2j, again, just by assumption, but that n squared is also equal to 2 times 2j squared plus 2j plus 1 by all our logic, right? So obviously this is a contradiction because 2 squared equals 2j means that 2 squared is even, but our other case, which we got through logic, shows that n squared is odd. A number can't be even and odd at the same time, obviously, so this is an obvious contradiction, and we're done with our proof. Let's do our final example with rational and irrational numbers. Our theorem is the sum of any two rational numbers is rational. So once again, we'll rewrite our theorem as an if-then statement. So I would say, if there are two rational numbers m and n, then m plus n is also rational. And so you might see that you can do this proof by direct proof. And most times I would actually say just do it by direct proof. But if your teacher asks you to do a proof by contradiction, you can definitely do it with this example. So we say that we're proving by contradiction, and we state our assumptions that the theorem is false. So our statement now is, assume that there are two rational numbers m and m plus n is irrational. So let's state our definitions first. Let's say m is equal to k over j for some integers j and k such that k is not equal to 0, and then we do the rest of our things like we've been doing in the other videos about proofs. Next, we plug our definitions into our statement. So we say that m plus n is equal to j over k plus u over v. And now you can kind of see that this doesn't look like one number by itself, right? It definitely looks like two terms. So we do some manipulations on it. In particular, we multiply j over k by v over v. That's the same as multiplying it by 1, right? So we don't need to multiply both sides of the equation by v over v, because multiplying a single term in an equation by 1 doesn't change anything. So if we multiply the first term by v over v and the second term by k over k, that gives us something with like denominators, which we like, because then we can just combine our two terms into being jv plus uk over vk. So then we've kind of come to the bit where we can make some conclusions about the numbers that we've gotten, right? So now we can make some conclusions about our numbers, right? So by assumption in the beginning, we said that m plus n never equals p over q for pq some integers, but we've literally just found out that m plus n does equal p over q for some p equals jv plus uk, which is an integer, and for some q, which is equal to vk, which is also an integer. So m plus n can't be both equal to and not equal to some p over q at the same time. So this is an obvious contradiction, and we're done. Yay! Hope this helps, and see you again in another video.